All right, we'll talk about this. And so, in the atom, chromium atom, for example, they're going to be orbitals. Orbitals are the allowed states for the electron. And so, what are the orbitals? What's the lowest energy orbital possible that an electron can occupy in a chromium atom? Lowest. Someone have it? Just take a guess then. Just guess one of the orbitals. You know any orbital? You gotta have 1s. Well, that's a good guess because the 1s orbital is the lowest energy orbital. So I'm glad somebody recognizes. This is going to be the lowest energy orbital possible. What does a 1s orbital shape look like? Spherical. What does that sphere represent? Lowest energy, the 1s, and also the probability. That circle represents the probability boundary for, what's the percentage? 95%. 95% probability that the electron is going to be found within that sphere. The nucleus is in the center. There's 24 electrons, so the way we represent electrons is by arrows. We have to pay attention to the Pauli exclusion. We want the ground state. The ground state just means the lowest energy possible. So if we have 24 electrons, we're just going to fill them. Can we put all 24 electrons into 1s orbital? No. What's the maximum capacity of it? No. Two. Two according to what principle? Pauli exclusion principle. Pauli exclusion principle tells us 2. Not only that, it tells us that these 2 have to be the same spin orientation or opposite spin orientations. Opposite. So we can fit 2 there. What are the quantum numbers for this first electron here? Tell me the 4 quantum numbers for this first electron. Yeah, 10 is correct. Keep going from there. 10. No, it's 1 0. What's the third quantum number? The quantum numbers are n, l, m, and s. So we have 10. What's m? It's 0. And s? 1/2. So this first one's 1 0 0 1/2. What's the second one? What do the first 3 quantum numbers tell us? The first 3 quantum numbers are like an address. They tell us the orbital, which orbital it's supposed to be in. It's in the 1 0 0 orbital. And the last quantum number tells us if the arrow's pointed up or if the arrow's pointed down. If the arrow's pointed up, we call it plus 1/2. If the arrow's pointed down, we call it. And so the address is the same. Both of these occupy the same address, 1 0 0, because it's the 1 0 0 orbital or the 1s orbital. And this one will be a negative 1/2. So this one's a 1 0 0 negative 1/2. And so we can identify each electron in chromium with a unique set of 4 quantum numbers. That's what Pauli exclusion principle also says, that every electron in chromium will have a unique set of 4 quantum numbers. Well, that takes care of 2. The third electron's got to go into a what orbital? Yeah, well, the next higher energy orbital, because we ran out. What's the next higher energy orbital? 2s. Draw a single line. And then we'll just fill it. 1, 2 electrons. So what would you call the first one? What are the 4 numbers for the first one? 2, 0, 0, 1 half. And the second one? Would be
2, 0, 0, negative.
Yeah, 2, 0, 0, negative 1 half. Okay, that's 4 electrons. We have 20 more to go. What's next? What's the next higher energy? Will be the 2p's. How many 2p's are there?
There's 3.
3. Yeah, 1. 2p's. Now, tell me, what is Hund's rule? Hund's rule is applicable to p orbitals and d orbitals and f orbitals.
In E, you can only do 1.
Yeah. We just do 1 at a time, and with opposite spin or parallel spin?
Parallel.
With parallel spin. So this 1, 2, 3, 4, 5th electron is going to go into 2p. What would you name that one? Give me the 4 quantum numbers for that one.
2, 1.
Yeah, it depends on how we name these individual orbitals. Let's go ahead and name the orbitals first. This one would be called a 2, 1. It doesn't matter 1 or negative 1, but I want from negative to positive, so we'll just do 2, 1, negative 1. The next one will be a 2, 1, 0, and the last one will be a 2, 1, 1. And so these correspond to the p on the x-axis, the p on the y-axis, and the p on the z-axis. You know, it's just depends on how you orient it. They're the same energy, and so this could be a what would you call this electron? This would be a 2, 1, negative 1, 1 half. And then where do we put the next electron? The next electron can go on either one of these. It doesn't matter because they're just orthogonal to each other, 90 degrees. So it's the same. This one's 90 degrees to that one. This one's 90 degrees. Just one's like on this axis, the other's on this axis. So the same energy. And so the next electron is going to go here, Hund's rule. And the next electron is going to go here, Hund's rule. And so now we're at 2, 4, 5, 6, 7. 8th electron is going to go here. We'll have to pair it. This is called pairing. Hund's rule, we avoid pairing until we have to. Now we have to pair it. We'll pair this one. We'll pair this one. And so the 1, 0, 0 orbital, this is the 1, 0, 0, this is the 2, 0, 0. All right, so we filled the first shell. Now we filled the second shell. And we got to keep going, right? We're going to go into the, what's in the next shell? What orbital do we get into the next shell? The 3s. Hey, did I miss something? Did I miss the 1p orbital? No, I didn't. Why? There's no such thing as 1p. Why is that? Why is there no 1p orbital?
That means L is 1.
Yeah. If n is 1, L cannot be 1. That would exceed the maximum L value. If n is 1, the maximum L value is what? 0. N minus 1. 1 minus 1 is 0. So I can't have an L equal 1. L equals 1 is a p orbital. If n is equal to 2, what's the maximum L? This is is L equals 0 here, and then L equals 1 here. If n is equal to 2, what's the maximum L? 1. And so I'm allowed all. So I have L equals 0 is allowed, L equals 1 is allowed, L equals 2 is forbidden. Call that forbidden. If n equals 3, then L can be equal to 0, L can be equal to 1, and L can be equal to 2, but L cannot be equal to 3 because that would exceed it. And so for the 3s, we're also going to have 3p. You know, the 3s is the 3, 0, 0, 3p, L equals 1, so we've got 3, 1, negative 1, 3, 1, 0, and 3, 1, 1. But what about the 3d? The 3d, do they go in the third shell or do they go in the fourth shell? They go in the fourth shell, so the 3d I'm not going to write here because the 3d get popped up into the next shell. And so let's fill up the third shell here. And so this is the first shell. First shell only has one subshell. The second shell has two subshells, the S and the P subshell. People call these levels too. The second level has two sublevels, the 2S sublevel and the 2P sublevel. The third level, or the third shell, has two subshells. You know, the third energy level actually has three sublevels, but the 3D gets popped up here. And so the jargon's kind of confusing. But anyway, let's fill this up. In fact, to fill up the first shell takes 2 electrons. To fill up the second shell, how many electrons does it take? 8. We call it an 8. 8 electrons, an octet of electrons. So to fill up the second shell takes an octet of electrons. To fill up the third shell takes how many electrons? Well, it'd be the same because we got 2 for the S, and then 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons there. 2, 4, 6, 8. And so now we're up to, how many electrons do we have? 2 plus 8 is 10, plus 8 is 18 electrons. We got 18 electrons up to here. And so we got to go up to the next shell. The next shell is going to start with what orbital?
4s.
The 4s. 4s. Put that here. 4s of the 400 orbital.
And you said that the 3D goes in the 4th shell?
3D goes into the 4th shell.
It will go there.
It's going to go above the 4s. In terms of energy, we do it like this. If we ever wanted, third energy level has 3s, 3p, 3d. Fourth energy level has 4s, 4p, 4d, 4f. You know, this is L. L equals 0, L equals 1, L equals 2, L equals 3.
Why is it that the 3D can go like in the 3rd shell?
Why can't the 3D go into the third shell? The 3D can't go in the third shell because of there are quantum mechanical reasons for this. In Chem 1A, you'll learn more about this, but in Chem 4, you know, we don't get into it that deep. And so the reason is because of the way the probability distribution is distributed. In the 4s, it has a higher probability of being found nearer the nucleus than a 3D. And so 3Ds are kind of, they can get shielded from, you know, they want as much positive charge. If you're an electron, you want as much positive charge shining on you. But what happens is some of these other orbitals can block some of the positive charge from shining on the 3Ds. And it's called shielding. And so the reason why the 3Ds get popped up there and the 4s's get dropped down here is because of this, because of the electrical interactions, which we aren't going to get into. We're just going to learn this. This is the ordering that we're going to observe. And so you just memorize it. And so So it goes 4s, and then the next one will be 3d. So the 3d are the next L. The next L I'm going to put over here. So this is L equals 0, this is L equals 1, this is L equals 2. Over here. What are the quantum numbers for each of these 5 orbitals?
322.
Yeah, 3, 2, 2. Well, we'll go minus to positive. So 3, 2 minus 2,
3 2 minus 1.
3, 2 minus 1,
3 2 0.
3, 2, 0,
3 2 1.
3, 2, 1, and 2, 2. So we get 5 M values. We call those. And so now we got 18, 19, 20. We have 4 more electrons. It doesn't matter. We'll put these according to Hund's rule in any 4 orbitals. We'll just pick the first 4. 5. This is what we expect. This is expected. And this would typically be it. We'd expect that if you want to condense this, we can condense this whole thing into something called an electron configuration. This is the orbital energy level diagram, or just the energy level diagram. And we can condense this into a electron configuration. But we're going to lose a lot of valuable information if we condense it into an electron configuration, but it's more compact. And so what would the electron configuration be for this? Actually, let's complete the 4th shell. There's one more orbital and sublevel in the 4th shell, or one more subshell in the 4th shell. What is it? What am I missing here? The 4p. The 4p are going to be higher in energy. Here. And then that completes the 4th shell. The 4p are empty orbitals. There are no electrons in there. If we condense this into an electron configuration, it's just a compact way of showing the sublevels. The 1s sublevel is filled with 2 electrons. The 2s sublevel is filled with 2 electrons. The 2p sublevel or subshell is filled with 6 electrons. The 3s subshell, 2 electrons. The 3p subshell, 6 electrons. The 4s subshell, 2 electrons. And the 3d subshell has 4 electrons. Now, if I fill the first shell, that's equivalent to helium core. If I fill the second shell, that's equivalent to neon. If I fill up to the third shell has been filled. What does that correspond to? Argon. And so this is going to be argon. And so what we can do is we can make this even more compact. This is equal to the argon, we can call the argon core, 4s2, 3d4. It's not squared, it's just the 2 electrons in the S. We don't square. How did I get the argon on the periodic table? It's just when we fill the shell, filled shells are stable. Filled shells are stable. And so if we look at the periodic table is arranged in shells, right? Shells of orbitals here. Looking at the periodic table, we fill the first shell, which is the first row of the element helium. The second shell is the second period, or the second row. Fill it with 10 electrons, it's neon. If we fill this with 18 electrons, we're at argon. And so if we go up to here, this is the same electron configuration as argon. And so we're just using that abbreviation. We'll have argon and then 4s2, 3d. Yeah. Yeah, right. So this argon abbreviation is for 1s2, 2s2, 2p6, 3s2, 3p6, because that would be the electron configuration for argon. Uh-huh.
Is it always going to be the elements on that?
It's always got to be filled shells for the abbreviation. There are a couple of exceptions that you should know. You should know 2 exceptions, 2 important exceptions these here. Chromium and copper are two important exceptions. And both of these exceptions deal, like when we have a filled shell that's very stable, it's a complete shell of electrons, so it makes it stable. But subshells can also benefit from this stability, in particular D subshell. If I have a half-filled or filled D subshell, we'll see additional stability. Filled being better, filled being better, but half-filled is not as bad. And the way to think about this is like this. It has to do with symmetry. Like it's like this. Like say you have a cake like this. If you have a complete cake, then there's some additional stability with that due to the symmetry of this. And so we could cut it in half, like a half a cake. If we have a half a cake like this, we cut it in half. This doesn't show additional stability. That is, this would be equivalent to, let's say we have 5 orbitals like this, and we just fill half of them. Half of them like that. There's no additional stability, but we don't fill half of them like that because of Hund's rule, right? We don't pair. What we do is we fill these singly. These are the 3D orbitals here. According to Hund's rule, do we fill the d orbitals like that if I have 5 electrons? No. The way we fill that is like this. We fill these one at a time. So 1, 2, 3, 4, 5. This would be a half filled. This half filled means we don't cut the cake down the middle like this. We cut it down the middle across like this. And so when we get half a cake, it's going to just be like this. It'll just be cut around here. And then we have half a cake. It retains that symmetry. Well, the situation that we have here is this. We're one slice away from a half-filled cake. So somebody took out a slice like this. And so it upset that symmetry. This is it. This is 4 electrons. 1, 2, 3, 4. And so we're just one piece away from being a half-filled cake. And if we have that half-filled cake, then there's additional stability associated with that. And so the exception here is like this. We expected this, but what's observed is that one of these 4s electrons gets bumped up into the 3d. And so we take a slice or an electron from somewhere else, and then we use that to fill the cake. This. And so this is going to be bumped up. And so now we'll have a half-filled 4s. But more importantly, we'll have a half-filled 3d. The half-filled is better than having a slice cut out of it like this. Well, what if you have 2 slices cut out? And so what we observe is a different electron configuration. Well, we expect this electron configuration. The observed electron configuration is this. It's going to be argon 4s1. So we lost one of those 4s electrons, but we promoted it to the d. So it's going to be a 4s1 3d5 configuration. 4s1 3d5. 3D5. So this is one of the important exceptions you have to memorize. You have to memorize we're just one slice away from being half filled. What if we were 2 slices away? Well, vanadium would be that. Vanadium would be 2 slices away. So vanadium's not one of those exceptions. So, if we look at vanadium, the electron configuration for vanadium, 1 less electron, so it's going to be argon. We use the abbreviation here. Argon, 4s2, 3d3. So if it's 3d3, then we need 2 more electrons in the d to half fill the d subshell. But promoting 2 electrons is not going to happen. And so what's not going to happen is this. It's not going to go argon 4s0, 3d5. So we aren't going to lose that. That doesn't happen. So what it just does is it stays. You know, there's very little benefit to going to 3d4 from 3d3. The benefit comes in going 3d5, but to lose 2 electrons out of the s is not energetically feasible. So it doesn't happen. So this just happens for chromium. Here, just for chromium. Periodic table. So, chromium's here, vanadium's here. Manganese is already half filled. And so if we go to manganese, manganese we don't have to do anything. That's argon, 4s2, 3d5. Then when we go from manganese to iron, well, then we got to start pairing things up, otherwise we run out of room. And so with iron, we have to pair. Take a look. And so things work out, you know, that's just one exception. I mean, we would expect that what we see in black here, but what we observe is what was in red. Anyway, here, this is what I was trying to show earlier. Here's the first shell, it's a 1s. The second shell is a 2s2p. Third shell is 3s3p. Fourth shell, how do I know? Well, we can always look at the periodic table, or we can consult this little pyramid. But I just read it off the periodic table. The fourth shell is going to be the 4s, 3d, 4p. Fifth shell, 5s, 4d, 5p. Sixth shell is tricky. The sixth shell is going to be 6s, and then there's a gap here because they didn't want to spread this out and insert this. It's going to be 6s, 4f, 5b, 6p, the sixth shell. We go from there. So we get that from the periodic table. There. All right. So here, let's take a look at the electron configurations here. So this is just normal filling, you know. Scandium 4s2, 3d1, titanium 4s2, 3d2 after argon. Vanadium 4s2, 3d3, so we go d1, d2, d3. This should be d4, it should be 4s2, 3d4, but this is a exception you have to memorize. And then it reverts back to normal. 4s2, 3d, 5.
4s2, 3d6, 4s2, 3d7, 4s2, 3d8. This should be 4s2, 3d9. Why don't you draw the orbital energy level diagram for this one here and show me why it goes 3d10. 4s1. Those are the two. Everything else is normal, how you'd expect it to fill. And so go ahead and draw the orbital energy level diagram for that. We'll come back to it.